We're going to do a very small section on some of the definitions and understanding, but most of the work is just going to be on those calculations. And the thing that I've noticed with thermal is the ideas are quite nice. Oh, sorry. The ideas are quite nice, but the calculations, some of the multiple choice questions can be really, really nasty. So we're going to focus mainly on the 3.1 calculations. So that's all to do with thermal energy transfer, because those are the ones that are most common. Okay, so we're going to start off by defining specific heat capacity, which is also a point where lots of people lose marks because they don't get a completely correct definition. So this is defined as the energy change, and what most people miss is the per unit mass I should say required there. So it's required to increase the temperature. My mouth moves much faster than my pen does. Required to increase the temperature of a substance of a substance by 1 Kelvin. Okay. Again, we can just state the definition, sorry, not the definition, state the equation and define the symbols. So if we look at the equation we have in our data booklet, which is Q is equal to mc delta T, specific heat capacity is C. So I can rewrite it as C equals Q over m delta T. So Q is the thermal energy change, delta T is the change in temperature, and m is the mass. Now, what I would do in an exam is I'd normally give both the equation answer and the definition answer, just to make sure I get all the points. But from the equation, we can kind of see where this comes from. So the Q is the energy change, dividing by mass is per unit mass, and the delta T is for a temperature change of 1 Kelvin. Okay. If we make delta T equal to 1, then it's just the Q per unit mass, which is kind of what we said. Now, the other one which comes up less often, and I think that's, to be honest, I think it's on its way out of the syllabus at the minute, and it'll probably disappear the next time the syllabus changes, is the thermal capacity. Which is the same, but without the unit mass. So it's the energy change required to increase the temperature of an object by 1 Kelvin. And the reason I think it's on its way out, and to be honest, I doubt you'll see a question. You may get a multiple choice question on it, but I think it's quite unlikely. This equation isn't in the data booklet, but it's Q equals C delta T, and this is capital C. So C is equal to Q over delta T. And those of you who are comfortable with equations, you see that all I've done is I've combined the M and the C. So big C equals MC. So I would definitely say learn this one. Definitely learn this one. This one, if you're feeling interested, maybe have a think about this one, but I doubt you'll get a question on it. But just in case. The other thing to be careful about is we need to make sure units match. So, I mean, for those of you who've ever heard me talk about physics, units are such a key thing. So if C is in, again, square brackets for my units, let's say it's in joules per kilogram per Kelvin, then I need to make sure that my mass is in kilograms to match that. My temperature, well, changing temperature doesn't matter, but I'd always work in Kelvin. It's a better thing to do, I think. But then my energy given out is going to be in joules. So this is going to be related to my Q, and this is going to be related to my M. So if instead I had kilojoules per kilogram per Kelvin, my energy would be in kilojoules. And if this said joules per gram per Kelvin, I would need a mass in grams. So make sure C, Q, and M all match. So let's just make a note of that. So C, Q, M must match. Because otherwise you could do the correct physics but lose a mark unnecessarily just because you've been a little bit careless with your unit. So another very similar idea to the specific heat capacity is what we call the specific latent heat. So the heat capacity is to do with what we call a sensible temperature difference. And that doesn't mean that it's not reckless or crazy. Something that's sensible means that you would sort of notice a difference in temperature. If you put your hand over ice at 0 degrees C and water at 0 degrees C, they're the same temperature. So, I mean, that's just a word that scientists use, which I wouldn't worry about. But anyway, so specific latent heat refers specifically to a phase change. So it's the energy required. And actually, a very useful tip, whenever you see the word specific, that always means per unit mass. And then this is going to be to change the phase of a substance And what I would always do in an exam, just to sort of show off your knowledge a little bit to the examiner, I would also say at constant temperature. Because hopefully you should know that for any phase change, because all the energy we're putting into the system is going into potential energy, none of it's going into the kinetic energy. And temperature measures kinetic energy averagely. So if the kinetic energy on average is staying the same, the temperature stays the same as well. And again, let's use the equation that we have in our data booklet to signify this. So we got Q equals ml. So we get L is equal to Q over M. So there are two things that they're going to do to make your life hard. Number one, they're going to give you a combination of thermal changes. So there'll be some temperature change and there'll also be a phase change. The second thing they're going to do is they're going to give you multiple forms of energy. So either two things are changing temperature or phase, or you've got an electrical heater. Sometimes even we're looking at kinetic energy transforming to thermal energy, which we touched upon at the end of the momentum section. So what I'll do quickly is I'll look at how we would set up our method for multiple thermal changes, ask if you have any questions, and I'll look at the method for different energies. So, where's my pen? There we go. So, for multiple changes, what I would do, either on your exam or just on some rough paper, is set out a flow chart. So, for example, let's say I've got starting ice at minus 15 degrees C. Oh, let's go for minus 5. Sometimes my hands and my mouth also don't work on the same level. And let's say I want to end up with, let's make it complicated. Let's say steam at 100 degrees C. So the first thing I need to do, well, we hopefully are aware that boiling points and melting points are fixed. So for ice, it needs to reach 0 degrees C before I'm going to melt. So first we're going to have ice at 0 degrees C. That's like our second step, second stage. Then it's going to melt and make water at 0 degrees C. Again, the temperature doesn't change because we're just converting into potential energy. Then we're going to go to water at 100 degrees C. And this is like the opposite to when we have a phase change. Because all the energy is going into increasing the kinetic energy, we don't get steam at any temperature before 100 degrees C. I know some of you may be thinking, oh, what about evaporation? Let's ignore evaporation for now because we know that it's not really the precise definition of the phase change between liquid and vapor. And then I can go to steam. So once I've made it clear what the different stages are, I can give each one an equation. So this is a temperature change. So it's going to be Q equals mc delta T. This is a phase change. So this can be Q equals ml. And because it's going from ice to water, it's going to be the latent heat of fusion. So fusion is liquid solid. This one, well, now I'm changing temperature again. So I'm just going to write mc delta T. But be careful that this C is now the C of water, which isn't necessarily the C of ice. In fact, it's very different. Okay. Additionally, the delta T is different. So let's go for a different color so we're not getting too confusing. So this delta T we can see is going to be 5 degrees C. This one is 100 degrees C or 100 Kelvin. It's the same thing. But what will stay the same is this mass in all of these equations is the same. So same mass. And finally, we've got this, which is another phase change. So I can write Q equals ml again, but this time it's LV, where V stands for vaporization. And again, the latent heat of vaporization is very different from the latent heat of fusion. For any of you who do chemistry, so you know that going from solid to liquid, we have to start breaking a few of the interactions. But when we go from liquid to gas, all the interactions between different molecules, we're going to have to break all of those. So vaporizing something requires a lot more energy. And now what I can do is I can find the total energy. So Q total is just going to be the sum of all the Qs. So if I take mass on the outside, because it's the same for each one, I've got C ice times 5, because that was the temperature change here, plus the latent heat of fusion, plus C of water, I'll just put CW, because I'm running out of room already, times 100, plus the latent heat of vaporization. So what I've done is I've added all of these together, and I've just taken the mass on the outside because it's the same mass. But this would be the overall energy change. Now, hopefully, a question wouldn't give you this many changes. So actually, you'll probably find it easier doing a question than this diagram I showed you.